Hi everyone, in today's video we will try to understand how a perceptron works. So a perceptron is a linear supervised learning algorithm which can efficiently perform a binary classification task. So the predictions made by perceptrons are based on linear predictor functions. To understand the concept in a much better way, we will try to take a simple example of OR gate and walk you through the decision taking steps to build the classifier to classify the predictions. This is how an OR gate looks like. We have two variables x1 and x2. If either of the two variable is 1, the target comes out to be 1, and if both the variables are 0, the target is 0. However, we are going to encode the target of 0 being equivalent to -1, and this is for computational ease, which will become more clear as we proceed further. Now if we try to plot the OR gate on a 2D plot, and if we consider the x1 and x2 as both the axis, we can see that all the positive points and the only negative point are linearly separable. We don't know the equation of the line which separates both the positive and negative cases, but what we can see is we could explain the line, or we could represent the line in terms of unknown variables w1, w2 and b in this form, and our entire task will be to find the values of wi's. There are many ways to draw a line which will separate both the classes. We are not talking about a maximum margin classifier over here as we used to do in SVM, but we will be talking about any such line that separates both these classes. So our aim is now to find a model that fits the OR gate. We will keep this equation in mind and we will generalize our results a bit in the form of matrices. So we construct a matrix X where the first two rows correspond to x1 and x2, and we already have the weights w1 and w2 over here. Now if we observe this equation carefully and if we try to generalize it in the form of all the four observations we have for the OR gate, this actually resembles somewhat like this: xw is equal to 0, where there will be a third term in W, which will be B, as it is represented over here. Now, in order to make this equation valid, what we will do is we will introduce a column over here in X where all the terms will be equivalent to 1. So on doing so, if we multiply X with W over here, we can get something like this: W1 x1 plus W2 x2 plus B. And for introducing the intercept B, we have to include a column where all the values are 1. And consequently, we have the target values which were ones, as either of the two variables are 1, and -1 whenever both the variables are equal to zeros. So we will have two nodes over here for x1 and x2. These are the weights corresponding to x1 and x2. W1 corresponds to x1, W2 corresponds to x2. This is the bias term, and the entire decision will be based on the decision rule. We will consider one function, which is a signum function consisting of both x1 and x2 as input parameters. Depending on any value of w1, w2 and b, which we will eventually finalize, it will output the value of +1 if all these terms are greater than 0, and -1 if the equation of line is less than 0, and 0 if it is on the line. Now if we see the image carefully, which we just plotted, so this holds valid as well. So this was the equation of line which we were trying to find out. Anything to the right of the line is positive, anything to the left of the line is negative. Let's try to observe few things from assumptions we just made. We see that for y being equal to 1, the case represented over here, we can get correct result for our model if the value of z is greater than 0. And we will get incorrect result if the value of z is less than 1. This is so because if the value of z is greater than 0, the value of hz, the signum of z, which we just defined over here, will be equivalent to 1, and this will mean that our model predicted the correct output. Now if the value of z is less than 0, this will mean that the model predictions was -1, and this was actually not correct because the correct value was equal to 1. Now this will mean that if I multiply the value of y with w1 x1 plus w2 x2 plus b, basically the value of z over here, this is greater than 0. And similarly, if we multiply y, which is equal to 1, with the value of z over here, which is less than 1, this entire term will be less than 0. Let's try to understand whether such a relationship is possible for y equivalent to -1 or not. So again, for y equal to -0, we see that the value of z is less than 0, then the signum function will give the value as -1, which will mean that the model is able to predict correctly, and the predictions will be incorrect if the value of z is greater than 0, which will mean that model predicted +1 where the actual value was equivalent to -1. Here as well, as we saw in the previous statement, corresponding to correct value, this relationship is valid. Like we multiply y with w1 x1 or plus w2 x2 plus v, which is the value of z, and it is greater than 0. And for the incorrect predictions, this relationship is valid as well, as we were able to see in the previous case where y was equal to 1. Here the failure of our model will mean that we have the values of W1, W2 and B, which are actually the model weights and biases, which are not able to mimic the performance of an OR gate. Whenever such a thing happens, we will try to find new values of W1, W2 and B to get better results. So if we club both the scenarios together, we will be able to get a function which is now dependent on W, which is FW, and we can write it in the form of XW, Y transpose XW. So this entire part could be written in the form of XW, and we just multiply it with Y transpose. So this is exactly what we are trying to do. Like based on the observations, we were able to derive the equation of FW, and now we need to maximize it, which will mean that we need to maximize the correct predictions. So this is our objective now. We have to find the value of W1, W2 and B, which will be maximizing FW. We will do this by using the principle of gradient ascent. Since we have to apply gradient ascent, we need to determine the gradients first, and doing so is pretty easy. We will consider the function FW, which is defined over here, and we will partially differentiate with respect to W1, W2 and B. Let's say we take this function FW, this is the function FW we have, and if I partially differentiate with respect to W1, keeping everything constant, we get this summation wi xi1. Likewise, if we partially differentiate with respect to w2, keeping everything constant, we just get wi xi2. And similarly, if we partially differentiate with respect to b, which is a constant over here, we simply get summation of yi. So we expand the term to get something like this, but what we will do at this stage is to make sure that we represent the entire expression in the form of a matrix multiplication so as to ease the computation. So if we look carefully, this is how the gradient of f is going to look like. And on the basis of this gradient, we can now determine the gradient ascent weight updation rule, which will look like this. Like we will have the weight at nth iteration. We already have found out the gradient of FW over here, and alpha is the learning rate which we are going to determine or which we are going to select in the beginning before we are proceeding with the algorithm. And depending on different values of Wn, iteratively we are going to solve till a specified number of iterations uh, till we get the fair enough accuracy. So this is how we will do. So we will initialize the value of W0. We are going to select the value of alpha. We are going to select the value of number of iterations we need to run. We will recursively apply this gradient upgradation rule, or the gradient ascent weight update gradation rule. And at one point of time, we will terminate the algorithm. Since we know the algorithm, we can solve the entire process on pen and paper, but since we will need a lot of calculations to be done, we will write a small Python code to validate our results and see what values of W1, W2, and B we are going to get for the decision boundary. We will use the freely available Google Colab for our task. So we start by importing the libraries. We just need the NumPy and sklearn, and from sklearn we just need the accuracy score from the metrics. We are not using any other functionality of sklearn as of now. And for the perceptron learning algorithm, these two hyperparameters are needed, which is the number of iterations and the learning rate. Now we are going to represent the OR gate and its corresponding target in the form of variable x and y. And this x and y is exactly similar to the way we defined x and y in our discussion. Um, and if we just scroll up, this is how the value of x was defined. And that's exactly how we were able to define the value of x in the code. And exactly the value of y was defined in this way. We define the value of y as it is. Now we run this segment and we proceed further to define the misclassification. So misclassification is anything which is like 1 minus accuracy, and accuracy means if the predicted output is 1 and the actual output is 1, then we get the correct result, and if the predicted output is minus 1 while the actual output is 1, we get the incorrect result. Accuracy score is the number of correct predictions divided by total number of observations which are given. So we proceed further and we initialize our weights. Our weights are all initialized to some random values, 3, 1 and minus 3. And 3 is corresponding to W1, 1 is corresponding to W2, and minus 3 is corresponding to B. And we are going to run the process iteratively for number of iterations. Like for 20 steps, we are going to run the step iteratively. First, we try to find out the value of x into w, and this @ sign is done for matrix multiplication. So it will take the value of x and multiply it with the value of w defined over here, and then we do what we wrote in our notes as a decision rule. This was a decision rule which we defined, and this is exactly what we are trying to do over here. So what we are trying to say is, corresponding to every value in output, it's equivalent to 1 if the value of z was greater than 0, and if the value of z is less than 0, we consider it as minus 1. So this is exactly what we did over here as we did in the theory. And then we print the misclassification rate because we now have the outputs ready. We have the actual value in the term of y. We just call the function which we defined previously and find the misclassification rate. And we see the deviations between the predicted and actual results. And also try to find out few more metrics which we defined in our discussion and see how it actually works out when we perform the iterations. So we have an old value of w. We will do this step iteratively, and the iterations are going to be same as the one which we defined over here. Now if I scroll down a bit, we were able to define the weight updation over here. So this is exactly what we are trying to do. We take the old value of w, which is wn, and this is the learning rate which we considered over here, and multiply it with the gradient, and the gradient was x transpose y. So that was the main reason to convert the entire calculation which we were able to derive over here in the form of matrix, because the calculations over here in the code became a bit easy. This will give me the updated value of W, and we will keep performing it till we hit 20 iterations, or in case we are able to find the misclassification to be 0. Let me run the code and see what all values we get. So this is the first iteration we are going to get, and zero point 0.5 was the misclassification rate. Now if we see carefully, the model was able to predict the second observation over here, this observation, and this observation properly. The two observations were not correctly predicted. So we were able to find the value of yxw over here. Now if I go back to my theory, this is exactly what we are trying to find out, this y into xw. What it said in the theory is, if it is greater than 0, then the predictions are correct. And let's see all the places in yxw where it is greater than 0. So this term was greater than 0 because the prediction was correct. This term was again greater than 0, the prediction was correct. And both the places where it was either 0 or -2, the predictions were not correct. And then we try to find out y transpose xw. The function, if we go to the theory, this is exactly what we were trying to maximize. Now we proceed with the iteration 2. We had the old value of w as 3, 1, minus 3. This is what we initialized it. We get the new value of w as 4, 2, minus 2. And with this updated value of w, we proceed further and then see what predictions we are getting. Now, if we see the predictions carefully with this updated value of w 4 to minus 2, these are the predicted results, and this is the actual result. Now, the misclassification rate is 0.25, which is much less than the first iteration. And there was only one place where the predictions were not correct. All the other places the predictions were correct, and the value of y transpose xw, which was again, if I reiterate, this is the value of y transpose xw we were trying to maximize. It actually increased from 2 to 8, and then the old value of old value of w gets updated with the new value of w, which comes out to be 5, 3, and -1. Now we will proceed with this value of w to the third iteration, and at the end of the third iteration, we get no misclassifications because the actual results are this and the predicted results are this, which is identical to the actual result. And if we check the value of yxw, all these terms are greater than 0. We don't have any term less than or equal to 0. And also the maximization term which we were aiming to look at is coming out to be 14. It was 2 initially, then it increased to 8. Now it's coming out to be 14. Now the final weights are 5, 3, and -1. So we get the equation of decision boundary as this, and the decision rule will look like this. So it will be +1 because we defined the signum function before as well. When this entire equation of decision boundary is greater than 0, and this translates to 5x1 plus 3x2 being greater than 1. This -1 gets shifted to RHS. And we get the value of -1 when the entire decision boundary is less than 0, which translates to this, and 0 otherwise. Now let's see what exactly we get out of an OR gate if we use the decision boundary. So let's try to find the value of 5x1 plus 3x2 using the values of x1 and x2 over here. So by putting x1 as 1 and x2 as 1, we get 8. By putting x1 as 1 and x2 as 0, we get 5. By putting x1 as 0 and x2 as 1, we get 3. By putting both the terms as 0, we get 0. Now let's put this entire thing in the decision boundary and make a decision. So this term 8 is greater than 1. So 8 being greater than 1 gave me the value of 1. Again, this 5 is greater than 1. and again this 3 is greater than 1. So I'm just following the convention over here, which we just defined, and eventually we get a value of 0, and 0 is less than 1, and by that logic we will just use the signum function over here and we get the value of uh, this term as -1. Now if I compare the actual values of an OR, so 1 and 1 will give me 1, 1 and 0 will give me 1, 0 and 1 will give me 1, and both the zeros will give me a negative class or 0. So what we are able to do is, with a given decision boundary 5x1 plus 3x2 minus 1, we are able to model the OR class effectively. So this is how the node diagram is going to look like. So this is the value of x1 and this is the value of x2. This is w1 and this is w2 and this is the bias term -1. And eventually it is going to give the value of +1 or -1 as before. Now if I go to the code for once and change a few values, like if I change the initializer to 2, 1, -3, and run the code again, we get different values 4, 3, -1. So initially we got 5, 3 and -1, which led to this decision boundary. Now we are getting another decision boundary 4, 3, -1. Now if I change this value of w even further and we say that 1, 1 and -3, we will get a different decision boundary altogether. This will mean that the decision boundaries are not unique. They are dependent on the initialization of W, as I show over here. It also depends on one more important factor, like if I'm getting 3, 3 and -1 over here, now with the same initialization, if I go and change the learning rate to something smaller and we run the code, we are going to get a completely different um, weights which are actually going to satisfy the constraints. This means that the decision boundary over here is affected by three things. First, the initialization of W which we do over here, and secondly, the initialization of both learning rate and number of iterations we use. So in this video, we were able to model the OR gate using a perceptron algorithm. I will urge you to prepare notes while watching the video and pause as and when needed to make the understanding better, and try out the code with different set of parameters to understand the hyperparameter tuning in a better way, even though it's a very simple example. One thing which we were able to see over here is the fact that since we had a linearly separable data, we were able to get the convergence in a finite number of steps. We were able to get a convergence in 4 steps. We could get the convergence in more number of steps. In the next video, we will try to prove the perceptron convergence algorithm, which mentions that if the data is linearly separable, we will be able to get the convergence in a finite number of steps. Thanks for your time.